All right, welcome everyone. Let's get started. So today we're going to look at a few more examples of finding intervals of concavity and inflection points. And then we're going to see how we can use the first derivative and the second derivative to classify critical numbers as either a local max or a local min, or possibly neither. So we'll see that in the next learning outcome. All right, so let's continue on. So, in this unit of kind of optimization, we've been finding intervals of increase, decrease, finding intervals of concave up, concave down. So the process is very similar. And last time we left off with example 4 here. So the function x plus square root 2 times sine x, defined on the closed interval from 0 to 2 pi. And we looked at this function for intervals of increase, decrease. Now we're going to look at it for intervals of concave up, concave down. And so the first step for doing this is calculating the second derivative. So we're going to calculate the second derivative of our function here. And like we said, we've looked at this one before. And we calculated the first derivative. And we have it over there on the right. It's 1 plus square root 2 times cosine x. So let's use that to calculate the second derivative. And when we do that, we get negative 2 times sine x. So there's our second derivative. Now the next step, once we have our derivative there, we want to look at where the second derivative here is 0 and where our second derivative is undefined. So that's kind of the standard steps here. Find the derivative, then figure out where the derivative is 0 or undefined. Same goes for increase, decrease. We're doing the same steps here. So our second derivative here is negative square root 2 times sine x. That's always defined. So there's really no contribution here for our second derivative being undefined. Sine of x is always defined. So we don't have no division by 0, no square root signs where we might have a negative under there, no natural logs. So sine x is always defined. So let's figure out where the second derivative is equal to 0. And it's going to be helpful to remember what the graph of sine x looks like. So it's this periodic function here. And what we have graphed is there's a few interesting points to remember for the sine function. So it starts off at the origin. It hits its high point at pi over 2. And sine of pi over 2, we'll kind of write this down just to remember it. Sine of pi over 2 is equal to 1. That's where sine hits its highest point. And then it hits it a bunch more times, but that's one of the locations. Then at pi, the sine function hits the x-axis again. And then at 3 pi over 2, the sine function becomes negative. It hits its low point. So sine of 3 pi over 2 is negative 1. And then at 2 pi, we're back to where we started. We're back to 0. So it has this very periodic shape to it. And so if we're trying to figure out where the second derivative here is equal to 0, well, that really comes from, we can really do that by taking our second derivative, negative square root 2 times sine x, setting that equal to 0, and really that comes down to just figuring out where sine of x is equal to 0. Divide both sides by that negative square root 2. And looking at the graph of sine, we know that happens at 3 places. X equals 0, x equals pi, and x equals 2 pi. Those are the 3 places where this happens on this closed interval from 0 to 2 pi. Now it happens to happen at the endpoints, so we'll see what that means when we do our sine chart. And that's what we're going to do next. So let's keep those three x values in mind. And we're going to do our sine chart. So that's the next step. So we're talking about a closed interval. So we're in between 0 and 2 pi. And the other point that we found was pi, right in the middle there. So this is really splitting our interval up into two intervals. The interval from 0 to pi, and then the interval from pi to 2 pi. And what we're going to do is we're going to look at the sign of our second derivative on those two intervals. And so our second derivative was that negative square root 2 times sine x. So, we can write down the various factors of our function. So negative square root 2 and sine x. And then we'll see what that tells us about f prime or f double prime in terms of the sign. And then see what that tells us then about the shape of our function f. So, if we start with the easy factor, that negative 2 is always going to be negative. And then to determine the sign of the sine function, if we need to, we can use test numbers. So, pi over 2 is a possible test number that we could use. And 3 pi over 2 is another possible test number we could use for that second interval. Want to make sure that if you do use test numbers, make sure that they're easy to evaluate. And so we're just going through and filling out our sign chart now. And as we saw on the graph on the previous slide, we know that sine of pi over 2 is a positive 1. And then sine of 3 pi over 2 is negative 1. So in between 0 and pi, our sine function is positive. And then in between pi and 2 pi, our sine function goes below the x-axis, so it goes negative. So let's put that in on our sign chart. So we know it's positive in between 0 and pi, and then it's negative in between pi and 2 pi. And so our second derivative then is the product of those two. So when we have a negative times a positive, we get negative. And then when we have a negative times a negative, we get positive. And so for the actual shape of our graph then, we conclude that on this first interval, our graph is concave down, and then we switch to concave up. So we found we are concave up on the interval from pi to 2 pi, and then we're concave down on the interval from 0 to pi. And then what we're seeing is right in the middle there, we're at x equals pi, we're switching concavity. So that means we have an inflection point. So that's the next kind of part of the process here. If we're trying to figure out the inflection points as well, we want to identify the inflection numbers. And so these are the places where in our domain where we switch concavity. And what we're seeing here is that f switches concavity at x equals pi. So even though we found our second derivative was 0 at x equals 0 and x equals 2 pi, we do not have a change in concavity at those points because they're endpoints. So there's nothing on the other side of the interval, so we can't be changing concavity at the endpoint. So, technically speaking, this graph does not have an inflection point at those endpoints, 0 and 2 pi. So only there right in the middle at x equals pi. All right, so we found the inflection number. So the very last step then is to figure out the actual y value of our inflection point. So we go to our original function, right there, the x plus square root 2 times sine x, and we plug in our inflection number. So we're going to evaluate our original function at x equals pi, and we get, what do we get? Pi plus square root 2 times sine pi, and sine pi is 0, so this just ends up being pi. So we have an inflection point at pi, comma pi. So that's a point on our graph, and that's where we have an inflection point, change in concavity. All right, so just an example there for involving trig functions for concavity. Let's try one more concavity one, and this is our most complicated example. So we looked at this function before for intervals of increase-decrease. The function is x raised to the 2/3 power times 6 minus x raised to the 1/3 power. We did the derivative. Now we're going to find the intervals of concavity for this function. So the very first step, and this is where we're going to take up most of our time doing this, is to calculate the second derivative. So here's our first derivative. We have to do the derivative of that. And if we look at that, there's a quotient, there's a product, and there's chain rule. So as soon as you get having to use all of those different rules to do your derivative, you might start thinking about our technique of logarithmic differentiation. And that's what we're going to use here. So as soon as you get to those where you're pulling out all the stops, you're doing the quotient rule, the product rule, the chain rule, you could do it, but it might be a little bit quicker, maybe a little bit less work to try logarithmic differentiation. And that's what we're going to try here. So we're going to start with our derivative that we found, our first derivative, which was 4 minus x, and let's leave a little bit of room because the very first step for log differentiation, we're going to apply the log function to both sides. So let's leave a little bit of space there. So this is what we found for our first derivative. Very first step, we're going to apply the natural log to both sides. And why we do that is because the natural log function is going to get rid of those quotients and products and powers. We're going to be able to simplify this down quite a bit. So let's go through that. We're going to have the natural log of f prime on the left, and then on the right side, we're going to have the natural log of 4 minus x minus 1/3 times the natural log of x minus 2/3 times the natural log of 6 minus x. So I'm kind of doing all of the log rules there in one kind of step. So anything that's in the denominator has a minus in front, and then anything that has an exponent on it, the exponent's in front of the log. So there's our simplified log version. Now we do the derivative. So now we go through and we apply the derivative to each term. So on the left there, that's the implicit differentiation. So derivative of natural log is the reciprocal of whatever's inside times the derivative of the inner function. So we get this 1 over f prime times f double prime. Then if we go through, when we differentiate each of these log functions, we just want to remember that we have to use the chain rule. So for this first one, it's 1 over the reciprocal, or it's the reciprocal, 1 over 4 minus x. And then we take what's inside, multiply by its derivative. So that's chain rule. Then we have minus 1/3. Derivative natural log x, we can just do that one. That's 1 over x. Then we have minus 2/3. And then the same thing for the ln 6 minus x. We do the reciprocal, but then we have to multiply by the derivative of what's inside. So again, a chain rule there. And if we just finish differentiating, let's just clean up that right-hand side. We end up with negative 1 over 4 minus x minus 1 over 3x plus 2 over 3 times 6 minus x. So just finish differentiating there. All right, so now we actually want to solve for the f double prime. That's what we're trying to figure out. So we can get that by itself on the left if we multiply both sides by f prime. So that's what we're doing. We're multiplying this side by f prime, and then we're going to multiply the other side by f prime. And we're going to work with that term inside the parentheses here, because when we have all these different fractions, we want to get a common denominator. We want to try to consolidate that into one fraction, because we're going to be trying to figure out where f double prime is equal to 0. So we want to get those all into one fraction. And so the way to do that is with a common denominator. So for that first fraction, the common denominator, we can take the factors from each of our denominators that we have. So our common denominator, we want a 4 minus x, we want a 3, we want an x, and then we want a 6 minus x. So those are all of the distinct factors from our denominators. And so for that very first fraction, what do we have to put in there? Well, we had a -1 up there originally, but we also have to throw in then to the numerator a 3, an x, and the 6 minus x. Anything that we do to the denominator, we have to put in the numerator as well. Then for our next fraction, we want to have that common denominator. It was originally the 1 over 3x, so what did we have to kind of additionally put in the denominator? Well, we had to put the 4 minus x, and then we have to put the 6 minus x. And then finally, for that very last fraction, we had 2 over, well, we want to have the 4 minus x, the 3x, and the 6 minus x. So what do we have to put there in the numerator or in the denominator? Well, we had to put in the 4 minus x. The 3 was there, but we also had to throw in an x. So we're just working on getting a common denominator and consolidating all of this into one fraction. So if you have any questions as we're going through this one, let me know in the comments or the chat, and I can kind of go back and, if anything's not clear here. All right, so we have our kind of each of our fractions now individually with the common denominator. Now let's get them all into one fraction. And what we're going to do is we're going to multiply things out. So as we do this, we'll multiply, let's multiply everything out here. So we can take the -3x and distribute it to the 6 and the minus x. So we end up with negative 18x plus 3x squared. Then in the next numerator, if we multiply all that out, we'll get negative 24 plus 10x minus x squared. And then for the last numerator, if we multiply all that out, we end up with plus 8x minus 2x squared. And this is all over our common denominator. And then as we go through this, we can kind of simplify everything in the numerator now. So there's a question, are we missing a 3 in the denominator? No, we could have put an additional 3 down there. So when you're trying to figure out a common denominator, you only need the kind of all the distinct factors, essentially. So if we were looking at this, to get a common denominator, this term has a 3, this term has a 3. So we only need to put 1 3 in. If we wanted to, we could put 2 3s in, and the arithmetic would be similar, but you'd end up with the same result. But since there's only 1 3 in each of those denominators, we only need to put 1 3 in for our common denominator. If you want to put 2 in, you could do it. All right, so let's simplify that numerator now. And if we go through, it's kind of fun to do this. So if we kind of compare the similar terms. So here we have an x squared term. It's positive 3x squared. Then we have a negative x squared and a negative 2x squared. So all those x squared terms cancel. Then kind of look for just powers of x. We have a negative 18x, but then we have a positive 10 and a positive 8x. So all those end up canceling. And we're just left with that negative 24 on the top. So when we do this, we end up with our second derivative being 4 minus x. And let's actually put in now what f prime was. So that's kind of one of our steps with log differentiation. We want to put in what f prime was originally. So it was 4 minus x over x to the 1/3 times 6 minus x to the 2/3. And then let's write down what we found after simplifying the rest there. It was negative 24 over 4 minus x times 3x times 6 minus x. And there's still a little bit more simplifying we can do. So if we look, there's a 4 minus x term on the top here, and there's a 4 minus x term on the bottom of what we just worked with. So those 4 minus x's cancel. We have a negative 24 and a positive 3, so we can divide out a 3 there and end up with just a negative 8. So we end up with negative 8 over x to the 1/3 times 6 minus x to the 2/3 times 1 over x times 6 minus x. And we can just combine those individual powers of x and 6 minus x. So we have x to the 1/3 times x. So those become x to the 4/3. Then we have a 6 minus x to the 2/3 and a 6 minus x. So we add the exponents. 2/3 plus 1 is 5/3. So we end up with 6 minus x to the 5/3 power. So quite a bit of work there to get our second derivative. But we got it, and that's about as simple as we're going to get it. So good review. It's a good review of some of our more advanced differentiation techniques here, particularly log differentiation. All right, so now let's use that second derivative to figure out the intervals of concavity. All right, so we have our second derivative. We found it was -8 over x to the 4/3 times 6 minus x to the 5/3. And what we need to do is we need to figure out where is this second derivative equal to 0 and where is it undefined. And the way we do this is we have it as a single fraction, so we can look where the numerator is equal to 0 and where the denominator is equal to 0. So that's the nice thing about getting it all into one nice fraction is the fraction's equal to 0 when the numerator is 0, the fraction's undefined when the denominator is 0. So if we look at this, the numerator is -8, and -8 is never 0. So our second derivative here is never equal to 0. And then if we look at the denominator, well, the denominator is equal to 0 precisely at we set each of those factors. So we set the x to the 4/3 factor equal to 0 and the 6 minus x to the 5/3 term equal to 0. And if we solve each of those, we get two values, x equal to 0 and x equal to 6. So those are the numbers that we're going to plot on our sign chart. So that's the next step. Do our sign chart. And our function is defined at those numbers, so these are in the domain of f. So our original function is defined at those values. So when we plot them on our sign chart, let's use filled in circles here just to remind ourselves that they are in the domain of our function. We get three intervals here. So we get the interval from -infinity to 0, the interval from 0 to 6, and then finally the interval from 6 to infinity. We're going to figure out the sign of f double prime on each of those intervals. So let's write down the various pieces of our function, -8, x to the 4/3, and 6 minus x to the 5/3. And we're going to see what those tell us about f double prime, and then ultimately f. So start off with the easy one. -8, it's always negative. Just go right across. It's always negative. The next easiest one, x to the 4/3. Well, that 4 there in the numerator of our exponent, that means we have an even power. So at some point we're multiplying a number by itself 4 times. So if you multiply any number by itself 4 times, you're always going to be greater than or equal to 0. And so on every one of these intervals, always positive. And so the only one that we might need to kind of think about a little bit is that 6 minus x to the 5/3. And if we need to, let's use a test number. So we can use a test number for each of these intervals. So for that first interval, we want something less than 0. So -1 is always good. If we plug -1 into that 6 minus x term, we end up with +7 raised to the 5/3. It's positive. Then if we go to our next interval, t equals 1, we could use that as a test number. Plug that into that 6 minus x term, we end up with 5 raised to the 5/3, also positive. And then finally, go to that last interval, Maybe we use another test number, maybe 7. And if we plug 7 in, we get 6 minus x, which is -1. So we have -1 raised to the 5/3 power. And when we have odd exponents like that, a negative results in a negative. So -1 raised to the 5/3 power is -1. So we end up with a negative result there. And so what can we say then about f double prime? Well, when we have a negative number on that first interval, we have a negative number divided by 2 positive numbers. The result is negative. Then for that next interval, we have a negative number divided by 2 positives, still negative. And then finally, for that last interval, we have a negative divided by a positive divided by a negative. The result is positive there. So for this first interval, we're concave down. Then we remain concave down. And then finally, we go to concave up on that last interval. So let's write down what we just found. We're concave up on the interval from 6 to infinity. We're concave down on the interval from -infinity to 0, and then the interval from 0 to 6. And you might be tempted here to try to combine these two intervals because they both end up at 0, but we can't do that here. Since f prime does not exist at x equals 0. So if we go back, let's go back real quick. What is the first derivative? Well, the first derivative we had right here, and there is this term in the denominator that gives us an undefined derivative at x equals 0. So our derivative is undefined at x equals 0, therefore it does not have a defined concavity. Remember, for a graph to be concave up or down, it has to have a tangent line at that point. And if f prime doesn't exist, it doesn't have a tangent line, so we can't define concavity at x equals 0. So we have to leave those intervals split up. We don't have, our graph is neither concave up or concave down at x equals 0. All right, so we got to leave those. What about inflection points? Well, we want to look for where our graph changes shape. And we see that at x equals 6. We see that right here. We go from concave down to concave up. We have a change in concavity there, which means we have an inflection point at x equals 6. And x equals 6 is in the domain of our function, so we do indeed have an inflection point there. So if we were to actually find the y value plugs 6 into the original function. So go back all the way to that original function, plug 6 in, you get 0. So the inflection point is 6, 0. So there's our inflection point. Found the intervals of concave up, concave down, and then our inflection point. All right, so once you get to the sign chart part, it's not too bad. This one, the derivative, getting that second derivative was a bit of a challenge. So that's about as hard as we're going to see those. So, sometimes logarithmic differentiation, you might have to resort to that. All right, so let's go on. And we're going to kind of continue on in the same vein, but now we're going to find our critical numbers, so something we've been doing, for most of these sections, but then we're going to classify them as either a local max, local min, or neither, by using either the first derivative or the second derivative tests. And so we're going to go through all those examples we've looked at for increasing, decreasing, concave up, concave down. We're going to go through all those functions kind of summarize what we did and just classify the critical numbers that we found. And so to begin this, let's just remember back, one of the earlier things we talked about in this unit is our definition of critical number. And it really comes from Fermat's theorem that says if function f has a local max or local min at some x value, x equals c, then either the derivative is equal to 0 there or the derivative is undefined. And so that's how we got the definition of critical number. We knew to look at these places where the derivative is 0 or where the derivative is undefined. And so what we're going to see in this section is how to kind of finish that thought. So the question is, how do we find local extrema, local max and local min? How do we find those places? Well, Fermat's theorem gives us a place to start looking. It says look for those critical numbers because you might have a local max or local min there. So these critical numbers, they are possible locations. We're not guaranteed to have a local max or a local min there. But if we do, they have to happen at a critical number. So, we might have a local max or a local min at a critical number, but we might not. We don't know. And so the steps we're going to take to find local extrema, step 1, we're going to find our critical numbers. Those are the possible locations where if we're going to have a local max or local min, it has to happen at a critical number. And then the second part of it is we're going to test or classify those critical numbers. And that's the main focus of this section, is what are those tests that allow us to classify the critical numbers. And so we have these little example graphs up above that just show you, even if something's a critical number, we're not guaranteed to necessarily have a min or a max. And, well, let's look at them. So in this first one, the derivative is equal to 0. We have a local min. In the second one, the derivative is undefined at x equals c, because we have a cusp there, comes to a sharp point. But we still have a local min. In that last graph, the derivative is equal to 0, so it is a critical number, but it's neither a max nor a min. The graph just flattens out, but we don't have a max or a min there. It's neither. So just because something's a critical number, we still need to figure out, is it a min, is it a max, or is it neither? So those are the kind of the three options we're considering here. And so the tests that we're going to look at help us determine, do we have a min, do we have a max, or neither? And so the first one we'll consider is the first derivative test. So let's read through this. Let x equals c be a critical number. So we have a critical number at x equals c, and our function f is continuous. If f prime changes from positive to negative at x equals c, then we have a local max. If f prime changes from negative to positive at x equals c, then we have a local min. And if f prime does not change signs, well, then we have neither. It's not a local max or a local min. So let's just look at a few examples here of what's going on with this first derivative test. And let's think about our sign charts. So we're going to look at our sign chart for f prime. So for this first graph, we see that we have a horizontal tangent line. Our graph flattens out at x equals 2, so that means our derivative is 0 there. So we do have a critical number at x equals 2. On the left side, we're increasing, so it's positive. And then on the right side, we're decreasing, so f prime is negative. So we're increasing and then decreasing. And so what the first derivative test tells us is if we see that change from positive to negative, means we're going up, and then we're going down. And so this first derivative test just tells us what we're seeing here is that we have a local max at x equals 2. So if we go from positive to negative, we have a local max. What about that next one? Do our sign chart. We're seeing that our graph flattens out at x equals 2 again, so we have a horizontal tangent line there. So our graph flattens out. But then if we were doing a sign chart, what we would see for f prime is that our graph is decreasing on the left, so it would be negative. F prime would be negative on the left, and then it would be positive on the right. So f would be decreasing and then increasing. And if we kind of just draw in what a decreasing shape would look like and then an increasing, that's basically what the first derivative test is telling us. We have a local min. So we have that change in direction, essentially. We go from decreasing to increasing, we have a local min. So that's the first two points of the first derivative test. The last two is where we don't have a local max or a local min. So on our third graph here, again, the graph flattens out at x equals 2, so the derivative would be 0 there. But on either side, our graph is increasing. So we'd be going from positive and then positive on the right. So f would be increasing and increasing. And if we draw in our increasing kind of trend lines, our graph is going up and then it's going up. So we don't have a change in sign at x equals 2. So this is an example of what our graph might look like. It's neither. It's not a local max or a local min. It's still a critical number at x equals 2. Just happens to not be a max or a min. And then something similar for the next one here. This is another graph where we don't have a local max or a local min, but if we were to do our sign chart for f prime, what we'd be seeing is negative on both sides of x equals 2. So we're decreasing and then decreasing. So we don't see that change in sign. So for the first derivative test, we're looking for a change in sign at our critical number. And that tells us max or min. Now there is also a second derivative test, and this one sometimes is a little bit easier to use. The downside is sometimes it's inconclusive and we can't always use it. So sometimes the second derivative test is a little bit quicker, but you run the risk of it not producing a result. So the first derivative test you'll always get a result from. So that's the one to always go back to. Second derivative test might be a little bit faster, but you might not get a result. But let's read through what it says. So let's suppose x equals c is a critical number of our continuous function f. And then we also have to assume that f prime is equal to 0 at x equals c, and that f double prime is continuous. So right away, there's a few more conditions there for this test to work. If f double prime is negative at x equals c, then we have a local max. And if f double prime is positive at x equals c, then we have a local min. And if f double prime is equal to 0, then this test is inconclusive. So we might have a min, we might have a max, or neither. It's unknown. So it could be any of those. If the test is inconclusive, we can't say. It might be a min, might be a max, it might be neither. So you can't make any determination. But let's kind of look at why this test works. So let's look at, let's say we have a point x equals c. So this is some point on our graph, x equals c. With this condition that f prime of c is equal to 0, that means we have a horizontal tangent line at that point. So our graph does flatten out there. And let's consider the case where f double prime of c is negative. Well, if our second derivative is negative, what does that mean about the shape? It means we're concave down. So the only way we can have a graph that flattens out at that point while still being concave down is to have this sort of shape. So this is the only way we can have a graph that flattens out while still being concave down. And what the test says basically confirms what we're seeing. We have a local max at this critical number then. Let's consider the other options. So say we have a point on our graph, and that's at x equals c. We're assuming f prime of c is equal to 0. So again, that means we have a horizontal tangent line, so the graph flattens out there. But now for this one, let's consider the case where the second derivative is positive. If our second derivative is positive, that means we have a concave up shape. So let's draw in what our concave up shape would look like. And the only way to have a concave up shape while flattening out at that critical number is to have something like this. And so what we're seeing here, what the second derivative test tells us, basically confirms what we're seeing here, that we actually have a local minimum. So we can use either of these tests. First derivative test, second derivative test. Second derivative test, it might not be applicable. You might get an inconclusive result. But let's see what we have from those previous examples. So the examples we're going to go through next are all functions we've looked at in the last two sections for the intervals of increase, decrease, and then the intervals of concavity. And we're going to use some of our results there to figure out the local maxes and mins of these functions. So for this first example, we had the function 1/3 x cubed minus 2x squared plus 3x plus 1. And so if we wanted to find the local max and local min values of that function, basically two things we need to do. Find the critical numbers, and then we need to classify those critical numbers. So finding the critical numbers, this is something we've been doing for a whole bunch of times now. Figure out the derivative, figure out where the derivative is 0, figure out where the derivative is undefined. And we've calculated this derivative, and we found the critical numbers. So when we found that our derivative in factored version was x minus 1 times x minus 3. Setting that equal to 0 gave us two values for x. So our derivative was 0 at x equals 1 and x equals 3. Our derivative here does not have any quotients or anything like that, so there was no place where our derivative was undefined. And so we've done these calculations before, so I'm not going to go through them all again. I'm just kind of summarizing the results here. But what we found out was that our critical numbers then were x equals 1 and x equals 3. And that's because those were also in the domain of our original function f. So that's something we need to check here. Are those numbers that we found by setting the derivative to 0 and looking for where it's undefined, are they actually in the domain of f? And here they are. So those are our critical numbers. So that's the first main step. You need to figure out those. So figuring out the derivative, setting the derivative equal to 0, solving for x. Once you have the critical numbers, then the next step is to classify them. We want to test our critical numbers, and you have two options for how to do this. First derivative test or second derivative test. You don't need to do both necessarily. We're going to go through both just as practice here. And the nice thing about the first derivative test is if you're finding the intervals of increase-decrease, you can basically classify the local maxes and mins right off of your sign chart. So let's say we were doing the intervals of increase-decrease, and we did that for this example. What did we find? Well, we plotted our number line, and then we were looking at 1 and 3. That gave us the intervals negative infinity to 1, the interval from 1 to 3, and then the interval from 3 to infinity. And then we did our sign chart for f prime and saw what that told us about f. So we found that on the first interval, f prime was positive, then it went to negative, then it went back to positive. So in terms of our original function f, means it goes from increasing to decreasing and then back to increasing. And so we did all this for finding the intervals of increase-decrease. So we did all our work there. So we're just kind of summarizing it now. But if we look at this sign chart, what we can see is that if we're increasing, then we switch to decreasing, and then we switch back to increasing. And so having this sign chart, we can pretty easily classify those critical numbers. We can see that we have a max at x equals 1, and then we have a low point at x equals 3. And that's the first derivative test. So we're seeing that we have a local max at x equals 1 and a local min at x equals 3. What would the second derivative test tell us? So in order to do the second derivative test, well, you need the second derivative. So we've calculated that. We got 2x minus 4. And then to do the second derivative test, what you would do is you would plug in each of those numbers. So you'd plug in the critical number 1 into the second derivative. If we do that, we get 2 minus 4, which is negative 2. Now for the second derivative test, we don't really care about the actual number. We just care about the sign of the number. So it's negative. And if you draw in what the second derivative test when it's negative tells us we're concave down. So let's draw in the concave down shape. And what the second derivative test tells us is we have a local max. So it helps to draw in that concave down shape just to really reinforce what the second derivative test is saying. It says you actually have a local max. So confirms what the first derivative test tells us. And then if we wanted to test the other critical number, 3, we would plug 3 into the second derivative, and we'd get 6 minus 4, which is positive 2. To apply the actual second derivative test, we just note that this is positive, which means the graph is concave up, and then draw in what a concave up shape would look like. So something like that. And what the second derivative test tells us is when we have that concave up shape, we actually have a low point. We have a local min. And that confirms what we found from the first derivative test as well. We have a local min at x equals 3. So then to get the actual value of our function, we just want to plug those x values into the original function. So if I were to plug 1 back into this original function here, I would end up with 5/3, or 7/3 rather. So we'd get 1/3 minus 2 plus 3 plus 1, so that's 7/3. If we were to plug 3 into that original function to get the local min value, we would get positive 1. So what we're doing here is we're just plugging the original value, or we're plugging our x value into the original function. So that's how we get the actual local max value, is by going back to our original function and plugging in to find y, essentially. All right, so just example one there, if we were going to do either the first derivative test or the second derivative test, that's what we would have seen. Let's try another one. So one of the other examples we looked at was the function x to the fourth minus 4x cubed. So we've done all this work. We're just going to go through and kind of summarize it. So to find the local max and local min, we want to find the critical numbers. So to do that, we would calculate our derivative, which we did, and then factor it in order to make solving easier. And then when we set f prime equal to 0, what did we get? We got x equal to 0 and x equal to 3. And then looking for where our derivative was undefined, there's no division by 0, so there's no place where this function's undefined. So there was no contribution here. So the only possible critical numbers were at 0 and 3. And then we just want to confirm, and we did this, but we just want to confirm that those x values that we found are actually in the domain of our original function. So x equals 0 is, we can plug 0 into our function and get something that makes sense. And we can plug 3 in. We can plug 3 into the original function and get something that makes sense. So these are in the domain of f. So that's one thing we want to check. Are they in the domain of our original function? All right, so let's see if we were going to, let's try our second derivative test first, just to kind of change it up a little bit. So let's say we found our critical numbers and we wanted to determine, do we have a min or a max at those critical numbers? Let's see what happens if we were to use our second derivative test. So the second derivative here is 12x squared minus 24x. And then to do the actual test, we're going to take those x values and plug them into that second derivative. So if we plug 3 in, what do we get? We get 12 times 9 minus 24 times 3, which is 36. We don't really care about the number, we just care about the sign of the number. So this is positive, means we have a concave up shape. So draw in the shape, and that tells you then we have a local min at x equals 3. So that's what the second derivative test tells us. If the second derivative is positive, we have concave up shape, which means we must have a local min there. Okay. What about the other critical number? Let's plug 0 in. So if we were to plug 0 in, we would get 12 times 0 minus 24 times 0, which is just 0. So this is inconclusive. Second derivative test doesn't work for that critical number. Doesn't give us a result. We don't know if it's a min, max, or neither. So it could be any of those. So if that's the case, if that happens, then we have to go to our first derivative test and see what's actually happening there. And so we did our sign chart for this function when we talked about intervals of increase, decrease. And so what we found was that f prime was negative on the first interval and the middle interval, and then it was positive on that second or on that last interval, which means f is decreasing, decreasing, and increasing. And so what the first derivative test tells us is, and it helps to kind of draw in the shape here, if we're decreasing means our graph is moving down. We're decreasing, our graph is moving down, and then at x equals 3, we start increasing again. And so we have this change in sign from negative to positive at x equals 3. That means we have a minimum there. So it helps if you kind of draw in those trend lines and you see what looks to be a local min, and that's what we have, a local min. Now, at x equals 0, there's no change in sign here. We go from negative to negative, so the graph will flatten out, but it doesn't produce a local min or a local max. So at x equals 0, it's neither. So to kind of summarize our results, we found that we have a local min at x equals 0, at x equals 3, and then there is no local max. And we just note that at x equals 0, it's neither. It's not a max, nor is it a min. So there's no local max. X equals 0 is a critical number, but it's not a max or a min. And then to actually get the local min value, we would just take 3 and plug it into the original function. So we go back to our original function here and plug 3 into that. And if we do, we'd end up with negative 27. So that's our local min value. So you have a choice, first derivative test, second derivative test. First derivative test will always give you a result. Second derivative test might be inconclusive. But sometimes it's a little bit easier. All right, let's look at the other function we considered, the 2x squared over x squared minus 1. We want to find the local max and local min of this function. So the procedure is we'd find the critical numbers, and we did all this before. So you can kind of go back in your notes for back to our intervals of increase decreasing and see all our work for this. But we found the first derivative. It was negative 4x over x squared minus 1 squared. Setting that derivative equal to 0, when we have a fraction, that's where the numerator is 0. So that gave us x equal to 0. And then when we have a fraction, looking for where the fraction's undefined, we look at where the denominator is 0. And for this, we got two values, x equal to positive 1 and x equal to negative 1. We just want to make sure those are critical numbers. So we go and let's actually figure out if these are in the domain of our original function. And the only one of those is actually in the domain of our original function, and that's x equals 0. So that's the only one that's in the domain of f. So if we look back at our original function, if we were to plug 1 into this, we'd end up with 2 over 0. We'd have division by 0 undefined. So this function is undefined at negative 1 and x equals 1. So the only critical number that we have here is x equals 0. So when we did our sign chart, let's try the first derivative test. When we did our sign chart, we still had to plot all those different points. So we still had to plot negative 1, 0, and positive 1. But for the critical number, we used a filled in dot, just to remind ourselves that it's actually in the domain of our function. And then for those two other ones, we used open dots, just to remind ourselves that we still have to consider those, but they're not in the domain of our function. And so then we looked at the sign of f prime on those intervals, and we found that it was positive, positive, negative, negative. So f was increasing, then it was undefined, then it was kept increasing, then we started to decrease, then it was undefined, and then our graph continued to decrease. So if we draw in the trend lines, we're increasing, then we're decreasing, and then we're decreasing. And so the only change in shape or change in sign that we're seeing is at x equals 0. We go from positive to negative, And if we draw in our trend lines there, goes up and then it goes down, it looks like a max, and that's what our first derivative test says. We have a max there. And that's the only critical number, so there's no local min. Even though we had those other two x values that were close to being a critical number, because our original function is undefined, there's no way that we could have a max or a min at those values. So the only one that we have a max at is that x equals 0, and that's our only critical number. Now, what would our second derivative test say? Well, we happened in our concave up, concave down work, we did calculate the second derivative. We only have one critical number to test, so let's plug 0 into that second derivative. Now, normally, again, you're not doing both of these necessarily. You only have to do one of these tests. So it's up to you which one you want to use, first derivative test or second derivative test. Second derivative test is sometimes a little bit easier, but it can be inconclusive. If we plug 0 in, what do we get? We get positive 4 over negative 1 cubed, which is negative 4. What does that tell us about our critical number? Well, when we have a negative second derivative, draw in the concave down shape, and that should remind you we have a local max. And that just confirms what we already knew from the first derivative test. We have a local max at x equals 0. And then to get our value, our local max value, we're just going to plug 0 into our original function, and we would get 0 out. So again, that's just going back to our original function. We're plugging 0 into there to get the actual value of our function. All right, so finding critical numbers, and then so the step of finding the critical numbers is pretty standard for all of these. It's when you get to the classifying where you have some options, first derivative test or second derivative test. So in the interest of time, I'll leave example 4 for you to kind of go through. So we've done all the heavy lifting in terms of finding the critical numbers, calculating the derivatives, and all of that. So I'll leave example 4 as just something for you to kind of go back through and go through your notes from our increasing, decreasing section, and go through your notes for our concave up, concave down section. But what you should see is that we have a local max at x equals 3 pi over 4. So try this for yourself. You have all the work in your notes from the previous sections. But just confirm this for yourself. We have a local max at 3 pi over 4 and a local min at 5 pi over 4. And our value, the actual value of our function, is 3 pi over 4 plus 1. And for the other, it's 5 pi over 4 minus 1. So just see if you can actually go through our steps here and confirm that for yourself. So go back through your notes. All right, let's try just that last example we had just done of x raised to the 2/3 power times 6 minus x raised to the 1/3 power. So we found the intervals of increase, decrease. We found the intervals of concavity. Let's just kind of go through our results and see what's actually happening for this particular function. So we found the derivative. Figuring out where the derivative was 0, we see that we have a fraction. So that comes down to just where the numerator is 0. And we get x equals 4. And then figuring out where the fraction's undefined, we can just look at where the denominator is 0. And we can see that happens at x equals 0 and x equals 6. And then we just want to go through, those are our potential critical numbers. And we just want to go through and check, are they actually in the domain of our original function? And they are. So the domain of this function is all real numbers. There's no division by zero, there's no negative, there's no even roots, and there's no log functions. So that domain of that original function is all real numbers. So we have critical numbers at 0, 4, and 6. All right, so let's see what's happening if we were to apply our first derivative test. And if you're doing the intervals of increase, decrease, you basically have all the work for the first derivative test. So what did we do? Well, we plotted our numbers on our sign chart, and then we looked at the sign of f prime on our intervals. And what did we figure out for the sign of f prime? It was negative, positive, negative, negative. So our graph was decreasing, increasing, then decreasing and decreasing. And so what does our first derivative test tell us? Well, it helps to actually draw in kind of what the shape looks like. So we're decreasing, then we switch to increasing, then we switch to decreasing, and then we keep decreasing. So that's a really rough sketch of what our graph is looking like. But it's enough to give us an idea that here we have a change in, we do have a change in sign here. We go from negative to positive, and we have a min. Then we see that at x equals 4, we have another change in sign. We go from positive to negative, and if we draw in the rough trend lines there, we see that we have a max. And then at x equals 6, there's no change in sign, so it's neither. It's not a max or a min. So we see that we have a local max at x equals 4. We have a local min at x equals 0. And neither at x equals 6. So no max, no min at x equals 6. And then if we wanted to find the actual value of our functions at those local maxes and mins, we'd go back to our original function, which is right here, and plug in. So our local max would be whatever f of 4 is, and it turns out that it's 2 raised to the 5/3 power. So that's the actual max, local max value of our function. And then the local min value would be f of 0, and if we plug 0 in, we get 0. So that's the local min value. Now what would happen if we were to try our second derivative test? So the first derivative test always works. You're always going to get a result. What would happen if we tried the second derivative test? So we went through all that work to calculate the second derivative. Let's actually see. Let's try to plug 0 in to our second derivative. And if we plug 0 in, we're going to get division by 0. So the second derivative test is undefined, or the second derivative at 0 is undefined. So that means we can't use our second derivative test for that critical number. What about f double prime of 6? If we tried to plug 6 in, we'd also get division by 0 with the term right here. So again, if we have division by 0, that doesn't tell us anything. Our second derivative is undefined in this case, and we just can't use the test. So we don't get any result for those two critical numbers for the second derivative test. So we can't say what it is based on just the second derivative test alone. So if we started with the second derivative test, we'd have to go and try the first derivative test. X equals 4 would work. So I'll leave it for you to go and try the second derivative test for that other critical number, and you should see that it's a local max. All right, so really that's it. Now there's one kind of special case where we can say a little bit more, and that's if we're going through our work and we're looking at on an interval from A to B and our function's continuous. If we find that we have only one critical number, well, we can say actually a little bit more. Instead of saying that it's a local min or a local max, we can actually say that it's the absolute min or the absolute max. So we get a little bit more there, knowing that we only have one critical number on the interval. So if we have a continuous function f, if we're talking about a closed interval, like the closed interval from A to B, we've looked at this before. We're guaranteed to have both an absolute max and an absolute min. So if we have a continuous, and that's not how you spell continuous, if we have a continuous function defined on a closed interval, the extreme value theorem, our closed interval method, guarantees that we have both an absolute min and max on that interval. If we're talking about an open interval, well, then we really don't know. So the result's kind of unsatisfying. We just don't know if we have an absolute min or max on that interval. We might not. But if we have one critical number on that open interval, then we do have an absolute min or an absolute max. Maybe both, but we have at least one, possibly. So we get a little bit there. So we possibly have at least one absolute max or min. Still have to go through our tests and figure out, do we have a min or a max, first derivative test, second derivative test. But if we do have a local min or max, we can actually say it's absolute. It's the lowest value or it's the highest value on that interval. So we'll try a couple examples next time, just going through the process here. Of again, finding the critical numbers and then classifying the critical numbers. But it'll be very similar to all the work we've done so far. All right, so we'll stop there. And next time we'll see kind of how we're going to use a lot of these results. And we're going to be looking at kind of applications of these optimization techniques. So we're going to be going through really kind of word problems and seeing how we can use the first derivative test and the second derivative test to find the absolute min and the absolute max for a kind of a mathematical model. All right, so we'll stop there for today. Have a good weekend, and then we'll see everyone next week. And remember, we have our 5th recitation exam next week, so I'll be sending out your latest progress reports so you can kind of keep track of what learning outcomes from the last exam you still need to work on for the follow-up. So kind of expect that in your email inbox, sometime today or tomorrow. I'll also be posting midterm grades on your Hub Student Center, and those will be posted as either just satisfactory or unsatisfactory. And if you have any questions, you can let me know about that. So have a good weekend, and we'll see everyone next week.